everybody, and thank you for coming to my astronomy class today. My name is Kim Balukin. This week's topic is about black holes. Today we will be answering questions such as, what are they? Are there any near us? How do they even form? If you don't know a thing about black holes, then this is the lecture to pay attention to. 50 years ago, black holes were dismissed as science fiction, but not anymore. Originally, they were simply called a collapsar, but in 1967, a famous physicist named John Wheeler coined the term. Black holes are a very important topic to cover because they influence our solar system in more ways than you can probably think of. Let's start out with a definition. A black hole is an object with such powerful gravity that nothing can escape from it. What is odd, though, about the name is that it's not perfectly black. There is some energy that radiates from it based on its overall temperature and radius. This gravitational force is so strong that the escape velocity of it would need to exceed the speed of light itself. This means that no light, radiation, or material, once crossing the black hole's outer boundary, can escape. It is said that there are no other objects known that possess this type of power. The abnormally small radius, not its large mass, is the reasoning behind why the escape velocity is so huge. Have you ever heard of Schwarzschild radius? It does have to do with the radius of a sphere. Specifically, if the mass of an object is compacted within the sphere itself, it causes the escape velocity to be that of the speed of light, hence a black hole. Once something nears the black hole, there's a boundary line, if you will, that once you cross it, you can never return. At this point, the gravitational force is so strong that it prevents both matter and radiation from escaping. This is called the event horizon. Black holes are surprisingly often the brightest points in the sky because of this phenomenon. When light enters this boundary area, it is spiraling down towards the center, being compressed and heated by friction. This action is so hot it glows, which causes us to see this light. Remember that it is not escaping from it. It is simply being swallowed up so quickly, and with so much force it becomes hot, and the light is the effect we see. Sometimes the light is so bright that astronomers often mistake it for a nearby star. Once the dust, gas, or light passes the event horizon at this stage, we cannot see it, and it is permanently hidden from our view. Think about this example for a second. Lighthouses tell you where you are and that you should stay away from them. This couldn't be more true for black holes, too. Now that we know a basic definition of it, it is important to learn how they form. The formation of a black hole, as well as the black hole alone, is one of the most powerful gravitational accelerations in all of its existence. First, think of a star. It's not alive, but it follows the pattern through its existence. It exists by converting hydrogen within its core into helium, a process known as nuclear fusion. It creates an outward pressure that is essential in maintaining its atmosphere against the force of gravity. The fuel necessary to maintain the star's atmosphere cannot and will not be maintained indefinitely. As it ages, the ability for nuclear fusion to happen decreases, and eventually the core, where the hydrogen and helium were kept, becomes unbalanced and begins to contract. The contraction causes the core to reheat, and the energy pushes the star's outer layers outward, causing it to grow a bit larger each time. It goes from a normal star expanding to a red giant. After it blows off its atmosphere, it begins to contract into a white dwarf. Once it reaches the white dwarf stage, gravity continues to crush the matter in the star even closer together. As a reference point, the crushing of the gravity causes the core of the white dwarf to exceed temperatures greater than 1.7 million degrees Fahrenheit. The next stage it will go through will be the neutron star stage. At this time, the density of the star is so great that on Earth, 1 teaspoonful would weigh 1 billion tons. Everything else has been compressed to a point of undefined mathematical size at the center of it all, called its singularity. Any laws of physics that you've learned in your years, forget about them. They fail to apply to this mass. Time comes to an end and gravity is infinite. This is what is so amazing about black holes. Gravity is infinite, causing it to become so magnified that it sucks in everything. This is the point where we refer to it as a black hole. If you want to talk about extreme orbits and extreme gravity, you're talking about black holes. That's at the top of the list. Nothing has stronger gravity than a black hole. It is the mass of something a little more than the sun compressed down into a ball that's only a couple of miles across. I'd like to briefly mention another topic in regards to black holes. I feel that this is one of the most sophisticated yet confusing ones that we'll discuss today. Stephen Hawking provided for us a theoretical argument for the existence of a theory, if you will, called Hawking's radiation. In simplest terms, I'll try explaining it. Particle-antiparticle radiation somewhat explains itself. It is the radiation of a charged particle with the radiation of another particle with an opposite charge. If you can wrap your head around a virtual particle, this is what they're considered. What happens is that a particle-antiparticle pair appears close to the event horizon. One of the pair falls in, while the other narrowly escapes. The one that fell into the black hole must have had a negative energy, the antiparticle. This process causes the black hole to decrease in mass, although it looks to an outside observer as just another particle entering into the black hole. Little do we know at that moment that that was a negative energy particle. There is a constant self-destructing action going on all the time, which adds to the amazement of this phenomenon. Right now you may be asking, so if I can't see anything emitted from it, how do I know it exists? Are there any near me? Excellent questions. In 2011, astronomers witnessed one of the biggest explosions ever recorded. A flash of radiation brighter than 100 billion suns, a gamma ray burst. It was a spectacular event. The burst came from a supermassive black hole at the center of a distant galaxy. It had been dormant, but something had brought it back to life. Basically, astronomers can see the effects of it on their surroundings. Also, astronomers have made such great observations about distant universes. It revealed that some galaxies emit vast amounts of radiation from their central regions. These are known as active galaxies. It's found that a supermassive black hole lies through all of outer space. There's many of them. It devours every piece of dust and gas that falls into it. Those that are active release tremendous amounts of radiation, which creates powerful jets that shoot out from either side of the black hole. The jets are made up of high-energy intergalactic matter that is drawn near the event horizon of the black hole. This mass is superheated and ejected away from the black hole. This matter is not necessarily coming out of the black hole, although it appears to be. Astronomers now think that there may be 100 black holes in our galaxy alone, and an encounter with any of them leads to oblivion. Black holes are very massive, and there is good evidence to suggest that the centers of large galaxies are the hunting grounds of supergiant black holes that feed on entire star systems. These objects that are billions of times more massive than stars are called supermassive black holes. Active galaxies emit so much radiation that they can only be powered by black holes. Also, the rapidly moving matter that is orbiting the core at extremely high speeds requires huge masses of millions or even billions the times the sun's mass to prevent it from flying out of the galaxies. Astronomers have identified a number of black holes within our Milky Way galaxy. The most spectacular black hole, known as Sagittarius A, contains about 4 million masses, and the closest is Cygnus X1. It is located about 8,000 light years away. Our sun itself will never become a black hole. Its mass would have to be about 5 to 10 times the mass it already exists, or it already has. It will most likely form a white dwarf and shine until it loses its heat and dies off. Our galaxy almost certainly has a supermassive black hole at its center because astronomers have measured that the stars move as if they're attached to something very massive. And in 1995, Andrea Ghez of the University of California of Los Angeles reported seeing stars spiraling about something more massive than our sun. The stars were traveling at up to 10 times the speed of a normal star. Then they would eventually seem to disappear. The explanation was simply the fact that the star was sucked into something, possibly a black hole, or went behind something we cannot see around. We have little to fear, though, because this was happening at the center of our Milky Way galaxy, which is a mere 24,000 light years away. Space is a cosmic freeway. Nothing stands still. Everything moves around everything else, thanks to a single force, gravity. Black holes are said to be the craters of new universes. It's important to keep in mind that gravity is the force of attraction that spreads throughout the universe itself. It's the force that holds stars and solar systems together, and with something as powerful as a black hole, there's no doubt that it possibly created the universes. Astronomers are being led to believe that the growth of the massive black holes are an integral part of the growth of the galaxies. There seems to be a close connection between the formation and evolution of galaxies and the black holes within them. Black holes, as we know now, are essential to the evolution of the universe. For galaxies in which the mass of the central black hole has been measured, that mass closely relates with the mass of the galaxy's central stellar bulge, or the curve or bump in the solar system. As we have previously learned, as a black hole gains more mass, it grows. Could this attribute to the stellar bulge and ultimately the beginning of a growing universe? Could the Milky Way have begun like this? The end of a black hole could be because of evaporation or temperature or even consumption. It's important to remember that its consistency is made up of an extreme amount of matter that is super compressed, causing an extreme gravitational force. Surprisingly enough, black holes can actually consume other black holes. What happens is that they merge with one another, which gives the illusion that one is consuming the other. But recent speculation hypothesizes that black holes may evaporate over time. The mass of the hole determines the amount of time it would take to evaporate, such that if the mass is large, the time would be long, and if the mass is small, the time would be short. It's also thought that a black hole isn't continued to be fed by infalling matter. It would begin to shrink over time, thus taking away its basic characteristics of what makes it a black hole. The fate of a black hole by temperature is such. As time passes, the temperature will continue to fall, eventually approaching absolute zero, and eventually evaporating into space. And at that last moment of a black hole's life, when the explosion occurs, it's equal to 1 million metric ton hydrogen bombs. They really know how to go out with a bang. That sense of wonder is a human characteristic, and it seems to grow deeper as we gain more understanding about how and why things happen. Even though it may seem that we hold much information about a black hole, it's still the most mysterious thing in the universe to this day. Although the visible universe extends to 13.7 billion light years from us, that doesn't mean that the universe ends there. It only means that we cannot see what lies beyond it. I want to leave you all with a great quote I found said by Carl Sagan. He said, "The universe seems neither benign nor hostile, merely indifferent." I thank you for tuning in today to this week's lecture. The importance of this topic to take home is the power that a black hole contains and its ability to completely alter a universe is both a positive and a negative thing. Thanks again, guys. See you next week.